Hello my dear students, in this lecture we are going to see one numerical on Rankine cycle. This question I have taken from Ekeeda. There are 4 questions in this question, and all these 4 questions you can form 2 mark questions for gate examination. Means in single question actually there are 4 questions for gate examination. So let us understand this question. The question is a simple steam power cycle. Now here they have provided steam power cycle. Steam power cycle is nothing but Rankine cycle. Steam is used, means it is a Rankine cycle. Therefore, very first they have given it is operating on Rankine cycle, right? So while reading question only, we are going to draw temperature versus entropy diagram for the Rankine cycle. Therefore, we will draw here temperature versus entropy diagram. Temperature on y-axis and entropy on x-axis. Now let us again go back to the question. A simple steam power cycle uses solar energy for the heat in. Now the meaning of this statement is that whatever may be the heat supplied in the Rankine cycle is taken from the solar energy, right? That they are saying. Now then, so while drawing Rankine cycle on TS diagram, there will be a liquid vapor dome like this, right? So let us draw this Rankine cycle while reading the question. Now water in the cycle enters the pump as saturated liquid at 40 degrees Celsius. Now entry to the pump we have represented as 0.3. So let us draw this 0.3, which is saturated liquid state. Therefore this is a 0.3. They have mentioned the water in the cycle enters the pump as saturated liquid at 40 degrees Celsius. Means temperature at this 0.3 is 40 degrees Celsius. They have given T3 is equal to 40 degrees Celsius, right? And my dear students, from 3 to 4 there is a pumping, right? Therefore 3 to 4 there will be a reversible adiabatic pumping. That means entropy remains constant during 3 to 4, right? Again read the question. And is pumped to 2 bar, means after pumping at the exit of pump the pressure is 2 bar. Therefore we can say P4 is equal to 2 bar. P4 is equal to 2 bar, which is nothing but we can say 200 kilopascal. And my dear students, we know that P4 is nothing but boiler pressure, right? Exit of pump is always entry of boiler, and boiler is a constant pressure heat supply. Therefore from 4 to 1 there is a heat supply at constant pressure. Therefore here we can say P4 is equal to 2 bar is equal to 200 kilopascal, which is nothing but equal to P1, which is nothing but equal to boiler pressure. So let us read the second statement. It then evaporates in the boiler. See, means from 4 it then evaporates in the boiler at this pressure. Means at 2 bar only it will evaporate in the boiler. Means in boiler there is a constant pressure heat supply. That is P4 is equal to P1 is equal to boiler pressure is equal to 200 kilopascal, right? Then the entry to the turbine as saturated vapor and enters the turbine as saturated vapor, and exit of boiler is entry to the turbine. Therefore entry to the turbine is saturated vapor. Therefore from 4 to 1 the process will be like this, right? There will be 1, and my dear students 1 will be on saturated vapor state because 1 is the entry to the turbine, right? Then at the turbine exhaust the conditions are 40 degrees Celsius and 10% moisture. Now my dear students, 1 to 2 there will be a turbine expansion, and at turbine exhaust, that is 0.2, temperature is given 40 degrees Celsius. Therefore we can say T2 is equal to, which is nothing but T3, 40 degrees Celsius, right? And moisture is 10%. 10% moisture means 90% vapor. And my dear students, 90% vapor means dryness fraction will be equal to 0.9. Therefore here quality at turbine exhaust X2 is given 0.9. 10% moisture means 90% vapor, which is nothing but quality is 0.9, 90%. The mass flow rate is 150 kg per hour. Here mass flow rate is given, which is nothing but 150 kg per hour, right? Kg per hour. If I want to convert into kg per second, then I have to divide with 3600. Therefore 150 divided by 3600, it will be in kg per second. Now my dear students, here determine the turbine isentropic efficiency. Now my dear students, as they are asking turbine isentropic efficiency, means 1 to 2 the turbine expansion is actual turbine expansion, which is not isentropic. Therefore actual turbine expansion is represented like this, right? It is represented like this, and here there will be 2, and temperature at 3 and 2 is same. Therefore 3 to 2 like this, straight line, straight horizontal line. Therefore the 2 point we will find here, and condition at 2 is given, that is temperature at 2 is 40 degrees Celsius and quality at 2 is 0.9. These are the given. And as they are asking isentropic efficiency of turbine first question. Therefore, here A is efficiency of turbine is equal to question mark. Therefore, my dear students, means the turbine expansion is not isentropic. And if the turbine expansion is isentropic, the process will be 1 to 2 dash like this, straight vertical line. 1 to 2 dash, we can say here 1 to 2 dash is isentropic turbine expansion, right? And which is not there. Here they have given actual turbine expansion and condition are given at actual turbine expansion. And 1 to 2 is actual turbine expansion. Actual turbine expansion. And my dear students, they are asking here efficiency of this 1 to 2 process only, right? So we will find later. Then second question is the net work output during the cycle. What will be the net work output? Now net work output is nothing but area enclosed by the actual cycle, that is 1, 2, 3, 4 and 1 back, right? For this cycle, whatever may be the area enclosed by the cycle is nothing but net work output, that we have to find. Then the cycle efficiency. Now here C is cycle efficiency, means for 1, 2, 3, 4 and 1 back again, right? For this complete cycle, what will be the efficiency? Means they are asking efficiency of Rankine cycle. Therefore, C is efficiency of Rankine cycle, right? And question number 1 is efficiency of process 1 to 2 only, right? Then the area of solar collector needed if the collector picks up 0.58 kilowatt per meter square, right? Now here they are asking whatever maybe the solar collector is used, what is the area required for this collector so that the collector picks up 0.58 kilowatt per meter square. Now this value 0.58 kilowatt per meter square is called collector density. And while solving question number D, then I will explain what is this collector density. Here only I will write what is the collector density. CD collector density is nothing but 0.58 kilowatt per meter square. During solution, we will see what is this collector density. Don't worry about that. Right. Now, my dear students, let us solve this question one by one. Now, very first, our target is to find efficiency of turbine. Therefore, for first question, let us find efficiency of turbine. Now, here 1 to 2 is the turbine expansion, which is actual turbine expansion. And my dear students, turbine is a work producing device. As it is expansion process, therefore turbine is a work producing device. And work produced by the system is positive work. And whenever it is a turbine or work producing cycle, in actual condition, it will produce less work as compared to isentropic condition. Therefore, in theory lectures, we have defined this turbine efficiency, which is nothing but actual work produced by the turbine. Turbine efficiency is actual work produced by the turbine divided by isentropic work the turbine can produce. That is, isentropic work is nothing but maximum work that the turbine can produce. Right. Therefore, it is a ratio of actual work to the isentropic work. Now, actual cycle is 1 to 2. Therefore, it is the enthalpy difference between 1 and 2, H1 minus H2 divided by isentropic expansion is 1 to 2 dash. Therefore, isentropic work is H1 minus H2 dash. So, my dear students, here in this question, our target is to find H1, H2 and H2 dash so that we can find turbine efficiency. Now, my dear students, in actual examination, they will provide you steam table and values of these enthalpies corresponding to particular conditions. But here in this question, intentionally I am not giving you steam table. Here my assumption is that you will purchase steam table and you will keep this steam table in front of you and you will find these values in the steam table. Here also I am going to dictate these values, but here my purpose is to you must learn steam table. But already I have taken almost 25 to 26 questions on this topic in this series of lectures, and in each and every numerical I have given you values from the steam table, and in actual gate examination also they will provide you values from the steam table for these enthalpies. But here for this question particularly, by steam table, keep this steam table in front of you and look at these values, right? Whatever procedure I will tell you here, follow this procedure, you will find these all values. Now let us find one by one. Now h1 is nothing but 0.1, and 0.1 is nothing but boiler pressure, which is given 200 kilopascal. So my dear students, look at the steam table. You have to find steam table, right? And for add pressure of 200 kilopascal at a saturated pressure of 200 kilopascal, you have to find Hg value, because my dear students, this one point is on saturated vapor state. Therefore, you have to check Hg value, right? So let us find this Hg value at 200 kilopascal. Therefore, we can say this H1 will be equal to Hg at 200 kilopascal. So look at the steam table at 200 kilopascal, find Hg value, and you will find this value is equal to 2706.7 kilojoule per kg. Right, this will be the value from the steam table. I have taken these values from steam table because here I am sitting with steam table only, right? And I am hoping that you are also sitting with steam table which is open, right? Now my dear students, H1 we have calculated. Now our target is to find this H2, right? So my dear students, H2 is in liquid plus vapor state. Therefore, for H2 calculation, we can say H2 is equal to HF plus X HGF, HFG, sorry, HFG. Now all these values you have to look at point 2, which is nothing but at point 2 temperature is 40 degrees Celsius. So my dear students, again at steam table, in steam table look at these values at 40 degrees Celsius. Now here I am deleting questions so that we will get sufficient space for the solution, because all the given data we have written, so no need of question now, right? Now my dear students, from the steam table, if I find in the steam table at 40 degrees Celsius, we will say at 40 degrees Celsius from steam table, I will get values. This HF value I will find. Here I am writing these values which I am looking here. Right. At 40 degrees Celsius, I am getting saturation pressure. Saturation pressure, which is nothing but pressure at 2 as well as 2 dash as well as 3, right? Because it is a constant pressure process, because it is a condenser. 2 to 3 is a condenser, right? Therefore P sat, which is nothing but P2, which is nothing but P2 dash also, which is nothing but P3 also. Here I am finding this value as 7.384 kilopascal, right? This is a condenser pressure, also called condenser pressure, right? So my dear students, this is a condenser pressure, right? PC also we can write PC. And here I can find HF value at this 40 degrees Celsius will be equal to 167.57 kilojoule per kg, and HFG value, that is Hg minus HF, this value is Hg minus HF, will be 2406.7 kilojoule per kg, right? So let us find this H2. Therefore my dear students, this H2 will be equal to HF plus X2 HFG, which is equal to HF is 167.57 plus X2 is given 0.9, right? Quality is given 0.9 into HFG. HFG is given 2406.7, right? So my dear students, for this solution, if I solve this question, I will get H2 value, and this H2 will be equal to 2333.6 kilojoule per kg. This will be the H2 value, right? Which is also required to find turbine efficiency. Here H1, H2 we have calculated. Now H2 dash is our target, right? Once H1 and H2 is calculated, let us solve for H2 dash. So my dear students, here I will write somewhere H2. At the bottom I am writing H2 is equal to 2333.6 kilojoule per kg, right? Now let us solve for H2 dash, right? Now my dear students, here our target is to find H2 dash, right? Now my dear students, to find this H2 dash, we need to find first the quality at this 2 dash, because quality at 2 and 2 dash is different. Therefore dryness fraction at 2 dash we have to calculate, right? We have one formula. This H2 dash will be equal to HF plus X2 dash HFG, right? And all these values we have to check at 2 dash point, and 2 dash is nothing but 40 degrees Celsius. Temperature is 40 degrees Celsius. H2 is equal to T2 is equal to T2 dash is equal to T3, 40 degrees Celsius. So my dear students, at 40 degrees Celsius, already we have written this HF value and HFG values, but only we have to calculate X2 dash, right? So let us solve for this X2 dash. Now my dear students, 1 to 2 is isentropic turbine expansion, that is reversible adiabatic turbine expansion. That means we can say S1 is equal to S2 dash. Therefore my dear students, here we can write S1 is equal to S2 dash, right? And my dear students, S1 is nothing but the entropy at 200 kilopascal, which is nothing but saturated vapor state, that is SG value at 200 kilopascal. Therefore S1 is nothing but SG value at 200 kilopascal, right, is equal to this S2 dash is at 40 degrees Celsius. 2 dash is at 40 degrees Celsius, right? Therefore this S2 dash is nothing but we can say SF plus X2 dash into Sg minus Sf, and these values are at 40 degrees Celsius. These values are at 40 degrees Celsius. These values we will see from the steam table, and here I will write these values. Now if I am looking at these values correctly in steam table, this Sg at 200 kilopascal, which is nothing but S1, is nothing but 7.1271, right? This value is Sg at 200 kilopascal is 7.1271. It will be in kilojoule per kg Kelvin. Kilojoule per kg Kelvin, right? Is equal to, now this Sf value at 40 degrees Celsius. If I am looking correctly, Sf value at 40 degrees Celsius from steam table I will get as 0.5725. Unit is same, kilojoule per kg Kelvin. Unit is same, kilojoule per kg Kelvin. Plus x2 dash is unknown. Now again from the steam table at 40 degrees Celsius, if I look at Sg value, the value is 8.2570 minus Sf already we have calculated as 0.5725, right? So my dear students, in this complete equation, the unit of entropy is kilojoule per kg Kelvin. So my dear students, in this complete equation only x2 dash is unknown. So let us solve for this x2 dash, which will be equal to 7.1271 minus 0.5725 divided by 8.2570 minus 0.5725. From this I will get this x2 dash will be equal to 0.853. That is quality at 2 dash. For isentropic expansion at the turbine end, the quality will be 0.853. Right. Now if I put these values in H2 dash, then this H2 dash will be equal to HF plus X2 dash HFG. Now all this value 2 dash is nothing but at 40 degrees Celsius. Therefore these values we have to check at 40 degrees Celsius. So my dear students, HF value at 40 degrees Celsius we have already written here, and HFG also written here, right? So let us write down these values. Therefore HF is 167.57 plus x2 dash is 0.853 into HFG is 2406.7, right? From this we will get H2 dash. Let us find this H2 dash. I think the value will be 2220.4 kilojoule per kg. Kilojoule per kg. This will be the value of H2 dash, right? So my dear students, here we have calculated H2 dash, we have calculated H1 as well as H2. So let us put all these values in efficiency of turbine formula. So just now we have seen efficiency of turbine is nothing but H1 minus H2 divided by H1 minus H2 dash, and all values we have calculated, which are equal to H1 is nothing but 2706.7 minus H2 also calculated, which is nothing but 2333.6 divided by H1 is 2706.7 minus H2 dash. We have calculated H2 dash also, which is nothing but 2220.4. And if I simplify for this turbine efficiency, then I will get 0.7672. And if I want to convert this efficiency into percentage, I have to multiply this equation or this answer with 100, so that we will get efficiency in percentage. Therefore efficiency of turbine, that is isentropic efficiency of turbine, in percentage will be equal to 76.72%, right? And this is your first question. That is question number A, right? Now my dear students, let us solve for second question. That is question number B. Question number B is to find net work, and net work is nothing but, my dear students, it is work of turbine minus work of pump. And here turbine is from 1 to 2 and pump is from 3 to 4. So first of all we have to find work of turbine and work of pump. Now my dear students, here if I put enthalpies in kilojoule per kg, this answer will be in kilojoule per kg. This answer will be in kilojoule per kg. And my dear students, if I multiply this net work with mass flow rate, then it will become power. Mass flow rates, if I multiply with mass flow rate, that is work of turbine minus work of pump, it will become in kilowatt, and which is called power, right? So here we will calculate power, right? That we are going to multiply with mass flow rate in kg per second. That is kilojoule per kg. If I multiply this kilojoule per kg with kg per second, this kg will get cancelled. It will become kilojoule per second, and kilojoule per second is nothing but kilowatt. Therefore answer will become in kilowatt, right? So my dear students, we will calculate both answers, right? Now here work of turbine, we will see work of turbine. Turbine is nothing but 1 to 2, which will be H1 minus H2, right? This should be kilojoule per kg. This is the work of turbine in kilojoule per kg. Also, if I want to find work of pump, pumping is from 3 to 4. Therefore, enthalpy difference from 3 to 4 is work of pump. Therefore, work of pump is nothing but H4 minus H3. And again, as pump is a flow device, therefore this work can be written as VDP work, which is nothing but specific volume at 3 VF into dP, that is pressure difference. At 4 there is a boiler pressure, and at 3 there is a condenser pressure, therefore it is boiler pressure minus condenser pressure. And VF is specific volume of liquid at 3, right, which again we will get from the steam table. This VF value is from the steam table. Therefore work of pump, which is equal to H4 minus H3, right, is equal to VF. This is VF is nothing but, we can check VF value at 40 degrees Celsius from the steam table into pressure of boiler minus pressure of condenser, right. Now my dear students, this all values we have to calculate. S3, this S3 we can say HF value at 40 degrees Celsius from the steam table. Therefore instead of this S3, I will write here HF value. S3 is HF value at 40 degrees Celsius, but this value we have to check at 40 degrees Celsius, right. So my dear students, let us put the values. Therefore H4 minus HF value at 40 degrees Celsius, we have seen that is work of pump is equal to HF value at 40 degrees Celsius is nothing but 167.57 is equal to, now specific volume of liquid at 40 degrees Celsius, that is VF at 40 degrees Celsius. If I look at this value, if I am looking correctly, I will get this VF value as, this VF will be equal to 1.008 into 10 to the power minus into pressure of boiler. Pressure of boiler is P1, which is nothing but P4. We have seen this as 2 bar, which is nothing but 200 kilopascal, minus here condenser pressure is nothing but P2, which is nothing but P2 dash, which is nothing but P3. And from steam table, this value we have calculated as 7.384, right. So let us solve this. Therefore we will get work of pump, which is nothing but H4 minus S3. S3 is 167.57 is equal to, this value I will find 0. Let us find this value 0.1943 kilojoule per kg, right. So my dear students, here we got pump work. So again, by putting these values, let us find H4, right. If I want to find H4, now my dear students, H4 will be equal to pump work, that is 0.1943 plus S3. This S3 will go this side, which is nothing but 167.57. Therefore I will get H4 value, which will be equal to 167.76 kilojoule per kg. I am hoping that you are solving this question along with me. Now my dear students, already we have calculated H1, we have calculated H2, we have calculated H3, which is nothing but HF at 45 degrees Celsius, 40 degrees Celsius, sorry, which is nothing but 167.57 kilojoule per kg. And here we have calculated H2. Now let us find here net work output, right. So let us move forward. Now here I am erasing everything so that we will get sufficient space for the solution. And I am hoping that you have written all these values on your notebook, because here I don't have sufficient space. You have a lot of space. You have complete notebook for writing, right. So the next question is, question number B is net work output. Now net work output is nothing but work of turbine minus work of pump, and this answer we will get in kilojoule per kg, right. If I multiply with mass flow rate, that is m dot kg per second, mass flow rate into work of turbine minus work of pump, then this answer will be in kilowatt, right. So let us find in kilowatt, and for the answer in kilowatt, the net work output is also called power, right. So let us find this net work output in kilowatt. Therefore W net is equal to mass flow rate into work of turbine. Now turbine is from 1 to 2, therefore enthalpy difference from 1 to 2 will be equal to H1 minus H2, right, minus work of pump. Now pump is from 3 to 4, therefore this enthalpy difference H4 minus H3 will be the pump work. So let us put all values. Therefore net work output will be equal to mass flow rate is 150 divided by 3600 in kg per second into, now H1 we have calculated, which is nothing but 2706.7, minus H2 also we have calculated, which is nothing but 2333.6, minus H4 also we have calculated, which is nothing but 167.76, minus S3 also we have calculated, which is nothing but 167.57. So let us put all these values and let us solve for this W net. Therefore, from this, my dear students, this W net I will get equal to 15.55 kilowatt, because here we have multiplied with mass flow rate, and as we have multiplied with mass flow rate, the answer will be in kilowatt. And this is the second question, that is to find net work output. Now let us solve the third question, that is question number C, which is nothing but what is the efficiency of Rankine cycle, efficiency of complete cycle. Now efficiency is always net work output divided by heat supply, right, which is equal to net work output. Here if I put net work output in kilojoule per kg, then heat supply also we have to take in kilojoule per kg. And if I put this net work output in kilowatt, then we have to take this heat supply also in kilowatt, right? Therefore, here if I write work of turbine minus work of pump, then there will be a heat of boiler, because heat supply during the process is boiler heat, right? And if I multiply with mass flow rate, m dot of work of turbine minus work of pump, then I have to multiply with heat of boiler also m dot, that is heat of boiler, right? Therefore, my dear students, let us find this efficiency of cycle. Therefore, here W net we have calculated in kilowatt, right? This will be in kilowatt, then this will be also in, then this heat supply also we have to take in kilowatt. That means for finding kilowatt, we have to multiply with m dot, right? So my dear students, here the answer will become work of turbine minus work of pump divided by heat of boiler, that is heat supply. Work of turbine is H1 minus H2 minus work of pump is, which is nothing but H4 minus H3 divided by heat supply. Heat supply is from 4 to 1. Therefore, enthalpy difference between them is H1 minus H4. So let us put all values. Therefore, efficiency of this Rankine cycle, will be equal to H1. I think we have calculated 2706.7 minus H2 is 2333.6 minus H4 is 167.76 minus H3 is 167.57 divided by H1 is 2706.7 minus H4 is 167.76, right? From this we will get efficiency of cycle. So let us find this efficiency of cycle. Now my dear students, if I simplify this, the option C, that is efficiency of complete Rankine cycle, will be equal to, the answer will be, I think the fraction is 0.1469, right? And if I multiply this fraction with 100, then I will get efficiency in percentage. Therefore, multiply with 100, then answer will be 14.69%. This will be efficiency of cycle, which is question number C, right? Now, last question. Let us understand the last question. In last question, the collector picks up. They have provided collector density, right, which is nothing but equal to 0.58 kilowatt per meter square, right? This is the collector density they have provided. Dear students, the solar collector is used to supply the heat, means from process 4 to 1. The heat supplied in the boiler is nothing but taken from the solar energy, and this solar collector is having collector density of 0.58 kilowatt per meter square. Let us say there is a sun. Now, my dear students, here there is a sun. Let us say this is the sun, right? Here, this is our sun. Here, this is the sun. Now, from this sun, the solar radiations are coming on the earth. These are the solar radiations coming on the earth, right? And here there is a solar collector. Let us say this is a solar collector, and having this collector density CD, which is given, right? Now, my dear students, this collector density is nothing but heat collected in kilowatt per unit area. Whatever the heat collected in kilowatt per unit area, that means we can say this heat collector is nothing but solar heat collected per unit area. Therefore, heat collected will be equal to collector density into area. From unit also you can say it is a kilowatt per meter square. Meter square is the area, kilowatt is the heat, right? And now, my dear students, this heat is coming from the sun. Now, my dear students, the same heat is entering into the boiler, means whatever may be the heat of boiler, here the same heat is entering into the boiler, that is heat supplied to the boiler. Therefore, whatever may be the heat supplied to the boiler is nothing but heat coming from the sun. Therefore, here we can say heat coming from the sun Q, that is radiation heat coming from the sun Q, is nothing but heat supply in the boiler. Now here, as this heat is in kilowatt, because here collector density is given in kilowatt per meter square, therefore this heat will be in kilowatt. Therefore, this heat supply also we have to consider in kilowatt. Therefore, this will be equal to CD into area in kilowatt will be equal to mass flow rate into H1 minus H4, and this answer will be in kilowatt, right? So let us put the values. From this, we will get area is equal to mass flow rate into H1 minus H4 divided by collector density CD. So let us put these values, my dear students, and you will get area required. And this area is nothing but question number 4. This area we have to find as a question number 4. Therefore, this is the fourth question D. Area is equal to mass flow rate is 150 divided by 3600 into H1 is nothing but we have calculated H1 as 2706.7 minus H4 is also calculated, and we have calculated H4 as 167.76 divided by collector density they have provided 0.58. Now from this, whatever may be the area you are getting, this area will be in meter square. Therefore, my dear students, the answer for this question will be equal to collector area required is 182.4 meter square, and this is your fourth answer. So my dear students, this is how you have to tackle different questions in different way. Thank you, my dear students. In next lecture, we will see one more numerical on Rankine cycle, which was asked in previous year GATE examination.